So, can we match these enormously huge growing functions that we learned to build out of the horizontal arrows and fancy combinations of horizontal arrows? Well, here's where we need another crucial technique. I'm just going to call it f sub nu for now, because it's not quite going to fit into the scheme of f sub alpha, f sub some number of n. The new function of n, it's going to be a very clever idea. It's going to be a single new function, but when I put n into it, I'm just going to actually take the nth of my functions that I've already defined, this hierarchy of functions, and I'm going to put that as the index, and I'm going to put it into here. So it's a little bit like when we originally defined this, we took n and we put it into a repeater index, a functional power index, and into the input. But it's more profound than that. We're going to say I've created all these different functions, and I'm going to take the nth function, and then I'm going to take n and put it into it. So this is called diagonalization. And if you Google like Cantor diagonal argument or something, it goes back to Cantor in the 19th century, and it's immensely powerful in set theory, foundations of mathematics, theoretical computer science. And I'll tell you why it's called diagonalization. Let me insert a table here. That should be plenty. Okay. And so what I've got here is, let's say, I'm just going to calculate all, oops, I'm not going to populate this whole table. So here's f0, and I'm not going to calculate, well, these are easy to calculate, but I'm not going to calculate these guys. I'm going to say, let's just make a table with all the answers to that, oops, to that f0 function, dot, dot, dot. And then in the next row, I'm going to put in f1 of 0, f1 of 2, f2 of 2. After all, we've got something with two indices, the thing that labels which function I've created, and oops, and then the thing that labels what input it's getting. Oh, these are ones. I'm getting ahead of myself. Okay, dot, dot, dot. Okay, and then this would be f sub 2. I'm just going to put all those functions down here. You know, I can probably do this faster. Again, copy and paste. It's all about copy and paste. Now I just have to change these. Hey, that's faster. Wow, very clever. Okay. And I'm just going to do one more, and we'll get the idea. And let's see. I don't know if I can copy and paste a whole row. I'm not going to try it. But let's do that with 3. Okay, so these will be the values of the 3 function, except this will be 1. So I make a table of all the stuff I've done so far, and this is actually nice even for what we did before. Remember, like the values of f2 of 2, that's created out of the f1 function, but not just applied to 2, it's f1 of f1 of 2. So you actually, to create a value of one of these functions, you only have to use values on this row, but because we do this repeatedly, we actually have to use values that go way, way out to the right. But here's the diagonal argument. F sub n of n means just take this. Why is that? That's a 1. Sorry. Just take this value for 0, this for 1, this for 2, this for 3, and then here would be f4 of 4. Oh, it looks ugly because it's not in math mode, huh? Okay. And then here's f5 of 5, etc. And you go down the diagonal of this two-dimensional table. So it's a very common argument when you have some structure that's two-dimensional table, what happens when you go along the diagonal? And it can do some really profound things. Right now, it's a way to get a super fast-growing function, because not only as n increases, not only is the input to the function increases, but which function I'm using also increases. So that's pretty awesome. Now, it takes a little while to really realize how powerful that is, and I have to add one more trick to it. Because f nu of like 4, say, well, that isn't that impressive. It's just f4 of 4. That's a heck of a lot less than like f100 of 4. Okay, so that's not really that great. Well, f nu is going to eventually beat f100. as soon as this index gets to 100. So like f1000 f new of 1000. That's going to beat the pants off of f100 of 1000 because it's in fact equal to f1000 of 1000. So this is great if we allow ourselves to put in pretty big numbers for the arguments. It creates a super fast growing function. And for most purposes, that's really fine. When you're really doing this in a more serious way, rather than just having fun creating big numbers, what's the main comparison is the eventual growth rate of the function. Can I put in a big enough number so that this beats this? Absolutely. Just put in this input to match this or exceed this index. But remember the rules of the game that I'm kind of trying to play. I don't want to have to put in anything of any size at all into these functions, and yet I want it to create some ungodly huge number. So this is a little unsatisfying to just go this far. But diagonalization plus recursion will turn out to really rock. Okay, but first I want to get the more official name for f new because it makes contact with a beautiful area of fundamental mathematics, and that is ordinal numbers. In particular, the theory of infinite ordinals, or a tiny piece of infinite ordinals, and ordinal arithmetic. So that explains, you might have been wondering why I have these 4 stars in the number 4 here. I didn't use it the last video, but now I'm going to use it. This is the number 4, as visualized by, say, a 3 or 4-year-old. It's 4 objects. The number 4 just should symbolize the idea of 4 objects. And we're going to think of ordinal numbers, different from cardinal numbers. Ordinal is really that idea of counting in order. And remember, with things like successorship that I was talking about before, it's all about counting in order. 4 is the number after 3. And that's the number after 2, and that's the number after 1, and that's the number after 0 where there's no stars. So what I'm thinking of with this picture of the stars is it's 4 objects but laid out in a particular order. Okay, so that's the number 4. Now, here's already a much more powerful concept. It's infinity. And you might wonder why it's called omega. I'll tell you that in a minute. This is an infinite set. So this arrow is supposed to suggest just basically dot, dot, dots, an ellipsis. These stars keep going on forever in this direction. So it's the first one, and then the second one, and then the third one, and the fourth one, in order and never stopping. And when we think about this kind of infinity, it goes by a special name. We use a lowercase omega, and that's just the most basic, simple kind of infinity. There are other kinds of infinity, and that's exactly one approach to that is exactly what we're going to be talking about right now. But that is infinity. Now, I claim we can actually understand that there's multiple kinds of infinity, and that we can do arithmetic with infinity. But here's already, I'm going to show you an arithmetic with infinity that already might be unexpected. So to add 2 ordinal numbers, you basically just put them next to each other. So here's 1 plus omega. So that's the first rule of sort of pictorial ordinal arithmetic. To add 2 numbers, you just put them next to each other. But the second rule of ordinal arithmetic is the exact configuration doesn't really matter. I'm thinking if this is the first star, and then the second, third, fourth, fifth, on up to infinity. I can just rearrange that. I can take this star and just shove it in as the first in the chain. And that is the same as what we started with. That's omega again. It's just a line of stars starting with 1, 2, 3, and just going off to infinity. That's not really essentially different from what we started with. So this 1 plus omega was kind of fake. Because I can rearrange them, it turns out in ordinal arithmetic, 1 plus omega, this kind of basic infinity, is just equal to omega. So you might think, oh, well, maybe ordinal arithmetic never does anything interesting. Maybe it's always just omega, because after all, how many different kinds of infinity are there? Well, remember, these are ordered infinities. They're ordered patterns. And the way we're going to use them is that recursion, the kinds of stuff we're doing here, is all about utilizing an ordered pattern. And so here's where it gets interesting. You take omega, and instead of doing 1 plus omega, you do it in the other order. Omega, so you start with this, and then you count, and you have a list that never stops, and then you start over. You tack one on after all those guys have been included. So to be more technically precise, it's an ordering in which this new star is bigger than anything in here. And all these guys are in their usual order. That's a perfectly good ordering of an infinite set. It's actually called a well ordering, which is crucial to the actual theory of this stuff. You could Google well ordering or look in Wikipedia for well ordering to learn more. And it says that omega plus 1 is not equal to omega, because no matter how I try, this is not the same kind of ordering, because this guy, this star, has no immediate predecessor. There's no star that's right before it in the ordering. Any one of these stars, if I pick the 1,000,000th star, that's not the immediate predecessor of this guy, because there's a whole bunch more. So the rule, roughly, is an arrow, if you have something that's kind of a star after an arrow, that's qualitatively different from a star after a star. Okay. So that's omega plus 1. Well, why am I introducing all this weird, sophisticated stuff? It turns out to be exactly the right way to organize the next steps of this fast-growing hierarchy. F nu, I called it just F nu, but you know what? We needed an object that comes after all of the natural numbers, because this guy beats every single row, every particular row of this diagram by the diagonalization trick. So it should be, if it had a number to it, it would be the next ordinal number after all finite numbers, and that's omega. So in fact, I was calling it F nu, but it's really called F omega. And so the official definition is that F omega of n is F sub n of n. It's diagonal. It's the diagonal trick. Okay. And so you can just replace all the nus with omegas here. Okay. So, but I said that the diagonalization is a little bit disappointing, let's say, from the point of view of this this game of producing extremely huge numbers out of small inputs, because it doesn't actually produce the world's hugest number out of this. F404 is pretty decently big if you actually unpack it, but it's nothing like the stuff with the horizontal arrows that we had before with the Conway chained arrows. So, what about F omega plus 1 of n? What should that be? Well, you know what? We have a rule for that. F of anything plus 1. And that's why I used a Greek letter here. Because I knew secretly that this was going to have stuff that was not just finite numbers, but more interesting stuff. Ordinal numbers, infinite ordinals. Okay, this still makes sense. Okay? It still makes sense. It says that F omega plus 1 of n is just F omega done n times to n. This, I think, is really the key thing. This is where it gets cool. I mean, it gets super big after this even, but this is where it gets pretty impressive. Okay, so let's look at this. Okay. Oh, first of all, let's remember, just to make connection with like new up arrows and all that kind of stuff, this is bigger than 2 and then n minus 1 up arrows n. So this is something we had already done before. We had actually really done the diagonalization trick, essentially, where we put in the number of up arrows as something that changes, as well as maybe the things that are being up arrowed, the base and the sort of exponent slot. And so this isn't incredibly new, but it's an extremely elegant way to do this. It's just saying, oh, this is diagonalization. This is something that shows up in all kinds of areas of mathematics. So this is beating sort of arbitrarily big up arrows, but just with an n in here. It's definitely not beating stuff where we would put in up arrows with here and then net towers of up arrows. And so it's not beating Conway chained arrows yet. But let's see what happens with F omega plus 1. Let's see what extra stuff we get out of here. Okay, so we're going to have to do an explicit example here. F omega plus 1. Now, of 1 is not interesting. Of 2, it's not going to be super impressive, I don't think, if I recall correctly. That's F omega squared of 2. Okay. What does that mean? It means F omega of F omega of 2. Okay, and finally we can unpack what those F omegas are. That's the diagonal trick. That's F2 of 2. Now, if you remember F2 of 2, that was F2 of 2 would be 8. 2 to the 2 times 2, so 8. Okay. And so that's F omega of 8. Oh, hey, now we start to get an inkling of the power of this. That sort of, that label omega, that placeholder omega, is just waiting for these inner ones to be evaluated, and then that tells you which function to use. And suddenly, oh, it's the 8th function of 8. That's really big. Remember, that's bigger than 2 and then 7 up arrows, 8, which is already getting pretty substantial. And I only put a 2 in here. Okay, let's do one more example of f omega plus 1. F omega plus 1 of 3 is f omega cubed of 3. That 3 doesn't show up very well. Kerning is not particularly good here, but oh well. Okay, so that's f omega of, f omega of f omega of 3. Okay. So we're going to do that diagonal trick. Let's do a copy and paste. Okay, f omega of 3 is f3 of 3. Okay. What was that? Did I actually calculate that out? I think I did. f3 of 3 is this thing. Oh, man. Okay. That's going to go, let's see, I guess I have to put it in here. Okay, so put that in parentheses, and then I'm going to do f omega twice of that. Put one more parentheses. Okay, and now it gets pretty scary. Okay, that's f omega of f sub this thing. Let's see if I can do that. Again, copy and paste. It's all about copy and paste for all of this stuff. Whoa! Okay. So I haven't even gotten to the outer f omega yet. I'll do that in a minute. Okay, but I'm going to start approximating. Okay, that's bigger than, let's just approximate this as, what was it? A lower bound for this was like 2 triple up 3 or something like that. Yeah, oh no, 2 double up 3. And that's a pretty low, sad lower bound. So that's f sub 2 double up 3 of 2 double up 3. And it's really quite a bit bigger than that. And in particular, it's more important that this is bigger than that. Oh yeah, and then that all gets fed into f omega. Okay? Okay. So that would equal f sub all this stuff of all that stuff. So let's try to breathe deep and see what's happening. I've got this number, which is at the very least 2 double up 3. Okay, and it's really quite a bit bigger. It's a pretty darn big number, but not by our standards anymore. Okay, but I take the double up function. I take that f function and I apply it to itself, and then I put that into this guy. Let's try and express it all in terms of these double ups. Okay, so we've got let's see, this f sub, that's going to be at least a 2 up arrow, and I put this in that slot. Okay, -1, but you know what? I'm not going to worry about it. Well, I guess I'll put a -1, whatever. Okay, actually, let's not even worry about it. Let's say greater than, but kind of approximately. Okay, might not be exactly technically greater than. Okay, and then f sub this guy. Oh my god, this is incredible. Okay, I'm going to replace this f sub this guy, again with this number. Oh, that should have been a subscript. Okay, and so that's greater than, approximately, because there's this sort of stupid -1 issue. Take this thing, take 2, do an up arrow, and put that gargantuan thing in there, and then put it there as well. Okay, so notice what this is producing. It's producing exactly that iterated up arrow construction. You take an up arrow, a multiple up arrow construction, and then you put that in the up arrow slot. And you also happen to put it in this slot too, which doesn't do as much, but it does something. And then you put that calculation in the up arrow slot, and you put it over here. Okay, so let me make clear what the parentheses are. Let me put parentheses around that. Oh, and that's still, okay. Okay, there we go. That's a little clearer. So already, we're only using a tiny bit of what we're going to discover about ordinal arithmetic. It says that this function, f omega plus 1 of n, basically replicates iterated up arrows. Okay, and that is exactly sort of the basic level. That was that was 4-term Conway chains. And so a rough statement is that f, you'd have to maybe look at the Wikipedia to get a better statement. It's roughly dominates like 2 arrow n arrow 2, something like that. I'd have to look it up. Okay, but we're getting to the level at least of basic 4-term Conway chains, and we've only just begun. Okay, because once you start dealing with ordinal arithmetic, omega plus 1, you know what? I can add omega plus 2, guys. It's not that hard. It's just omega plus 1 plus 1. That's the basic idea of addition defined in terms of successorship. So I could have f sub omega plus 2 of n. That is this gargantuan function. Oops, that's not what I meant. Omega plus 1, this iterated up arrow construction, which is already starting to match some of the Conway stuff, f omega plus 1 of to the n, iterated n times of n. Okay, so, and what's that going to do? Let me unpack that just one more stage to emphasize how huge that's going to be. Because when we iterate one of these f omega guys, or f omega plus 1, it's not just that we're iterating one fixed function. We're iterating something that when we unpack these guys, we're going to get to the diagonalization step. And the diagonalization step suddenly puts whatever number is inside here as the index of the function. So let me just do one explicit example of here. Just unpack it part way. F omega plus 2 of 3 is going to be f omega plus 1 of f omega, oops, that's it, of f omega plus 1 of 3. Okay. Well, what is f omega plus 1 of 3? That means do f omega 3 times. Okay, f omega of f omega of f omega of 3. And now we can finally do the diagonalization step at least once. That's f3 of 3, which already is a pretty big number. That's that number with all the 2's and 3's that we had in the previous thing. Okay, and then we put that into f omega. So in other words, that's going to be putting this gigantic number into which function it is, which we know has a tremendous effect. And then that is going to be putting that into here. Oh, and it didn't subscript it. Okay. So I take f3 of 3, and I put that into the input slot and the which function slot. That's the diagonalization step. And calculate that huge number. And then I take that, and I put it into the input slot and the which function slot. And then this omega plus 1, that takes f omega, and it does it this many times. So I'm going to be writing, let's see, I'm going to be taking this, oops, and I'm going to be writing f omega of this, of f omega of, and I'm going to dot, 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 and f omega is the last one. And in the dot, dot, dots there's going to be this many of them. This a gargantuan number of doing f omegas, and every time I do an f omega, I do this thing of taking this number and put it in this slot, and then I take the result of that and put it in the function slot, put it in that in the function slot. So that is the combination of diagonalization and recursion, and it's super powerful. Okay, now if we actually go back to Conway, the Conway chained arrow notation actually has this combination in it of diagonalization and recursion up to a point. And so in the next video, I'm going to take this even further with ordinal arithmetic and these functions, and we're finally going to get past pretty much anything you could reasonably express with the Conway notation, which is pretty amazingly impressive if you remember how big those numbers were.